Let us start. Newton's second law of motion, as it is written here and rightly says that it is the rate of change of momentum is directly proportional to the applied force. So what is momentum? Momentum is nothing but mass into velocity, and momentum is always in the direction of the velocity. So change in momentum, of course, if there is a change in velocity, there will be a change in momentum, which is given by delta p is equal to m delta v. And rate of change of momentum, it is nothing but delta p by delta t, which is m delta v by delta t. So delta p by delta t, we know from the Newton's second law of motion, is the rate of change of momentum. It is equal to the applied force, and it is given by m into a, where delta v by delta t is nothing but acceleration. So I can say that rate of change of momentum is equal to the applied force, and it is given by equation F is equal to m into a. So force will be in the direction of the acceleration. So we will cover a small example. You can see here there is a mass m1 of 2.5 kg, to which a 10 Newton force is applied in the positive x direction. What is the acceleration in this case? I will apply equation F is equal to m into a, and 10 is the force, 10 Newton, 2.5 is the mass, a is the acceleration. So acceleration is 4 meter per second square, and of course it will be in the direction of x, as I have written here. So up to this point it is clear. Now I will extend this further by attaching one more mass to a string, which is m2. It is again 2.5 kg. So, and 10 Newton force is 10 Newton is applied onto mass m1 here, as you can see in this figure. Now I have drawn here is a dotted line, green line. So this is one system. So this one system in which there is a force, there is a tension T which is there in the string. So this tension T is nothing but it is an internal force for the system. So F is equal to ma is applicable for the external forces, and no internal forces come into account while applying the force F is equal to m into a. So the acceleration is responsible for net forces which is acting on the mass m, net external force acting on the mass m. So 10 will be nothing but 2.5 plus 2.5 into a. Acceleration will be 10 by 5, which is 2 meter per second square, which is in the positive x direction. Now I can draw the free body diagram, which I will continue to write in my videos as FBD. So FBD will always mean free body diagram. So here if I draw the free body diagram of M1, means I am depicting all the forces which are applied on mass M1. So I see there is a 10 Newton force which is applied in the positive x direction, and there is a tension T which is applied in the opposite direction. I will apply again F is equal to m1 into a. That is Newton's second law. So 10 minus t. I have taken 10 minus t. Why I have considered 10 minus t? I have considered 10 to be greater than t, and net force I have considered in the positive x direction. Therefore, it is 10 minus t. If I will consider net force in the negative x direction, then I can take t minus 10. So I will solve the equation with t minus 10 also, by assuming that the net force is acting in the negative x direction. So first I will solve it with the positive x direction. So 10 minus t is equal to 2.5 into a. 10 minus t is nothing but 2.5 into 2. 2 is the acceleration which I have already found out. You can see here. So 10 minus t is 5. So t is nothing but 5 Newton. Now if I consider net force to be in the negative x direction, then t minus 10 will be 2.5 into a. But here a will be minus 2, because acceleration we have found out in the positive x direction as 2 meter per second square. And now if I take as a negative x direction, then I have to use minus 2. So I have used minus 2 here. A is equal to minus 2. So which will make t minus 10 is equal to minus 5, 2.5 into minus 2 plus 10. So T is 5 Newton. So 5 Newton is the force. Again, it is acting in the minus x direction. I am going to further extend this example to by adding another mass of 5 kg to this. So you can see there is mass m1 2.5 kg, another mass m2 2.5 kg, and m3 is nothing but 5 kg. So they are all attached with a string. There is a tension T1 in tension T1 in the string between mass m1 and m2, and there is a tension T2 between mass m2 and m3, and 10 Newton force is applied. Now if I take this total green system which I am now making with the red, so it will be 10 Newton it will be a one system. So F is equal to m into A. So 10 is the external force applied on the system. T1 and T2 are the internal forces I have written here. So 2.5 plus 2.5 plus is wrongly written here. It will be 2.5 plus 5. So this will make it 10A. So 10 is equal to 10A. A is 1 meter per second square. Again, it is in the positive x direction. Acceleration is in positive x direction. So free body diagram of M1, I am again drawing 10 Newton is in positive x direction, tension T1 is in the opposite direction. So F is equal to m into A, 10 minus T1 is 2.5 into 1, 1 is the acceleration which I have already calculated here. So T1 is 7.5 Newton. And what about if I draw the free body diagram of M3? There is only one force T2 applied to it. M3 is 5, M3 is 5 kg. So F is equal to M3 into A. So T2 is 5 into 1. So T2 becomes 5 Newton. So this helps to solve the problem by applying Newton's second law. So you can now do the free body diagram of M2. This I am leaving the students to all of you to draw the free body diagram of mass M2 and find out T1 and T2. And for the simplicity, I can just draw the diagram which is here as T1 and T2, and I would request all of you to do this exercise and find out T1 and T2 by this method. Hope you would have understood the basic principle of Newton's second law and how it is useful in solving the problems. So we will cover more such examples in our upcoming videos. Thank you.